Okay, grade 11, so we're on to limiting reagents now. Please, heads up, this is not easy, and this is actually matric work. It will be examined in matric, as will all of your stoichiometry actually, but that was all done in grade 10, so it's not new, and it should be relatively unchallenging by now. So just this limiting reagents is going to be quite tricky. Please try your best, watch the video over and over again if you're stuck, look at that note over and over if you're stuck. I tried to make it as comprehensive as possible. Okay, so basically what this section is about is, up until now when you've had questions, they have usually gone ahead and told you information about one of your reactants. So they'll tell you we've got 100 grams of one of your reactants and excess of the other. So that means they've told you which one will run out first, basically. Now the progression of the reaction depends on which reactant will run out first, right? Now in this section, you're going to see questions where they give you information about both of your reactants. And before you can figure out how much product will form, you need to figure out, well, which reactant will run out first, because that will dictate how much of your product forms. Okay, so you're going to usually have, so this is just sort of a general reaction equation for the section. We'll have a limiting reagent reacting with something that is in excess to produce your product. Now they're not going to tell you which one is limiting and which one is in excess. You need to identify that. I will show you how to identify that a bit later on. But for now, just a few sort of definitions, how to understand what's going on here. Your limiting reagent, and your formal definition is in your notes, but your limiting reagent, this is the reactant or reagent. That's a good point. Reagent is just a fancy way of saying reactant, okay? So your limiting reagent, this is the reactant that runs out first, okay? So this dictates how much product is formed. Okay, so if the reaction stops when our limiting reagent runs out, then that means the product that forms depends on how much of this we have to react. Okay, so it dictates how much product is formed, and it's called limiting because it limits the reaction. Okay, it limits how long the reaction can go on, it limits how much product can be formed and how much of our excess reagents is used up. Okay, on to the next one, your excess reagent. This is your reactant that doesn't run out, basically. Okay, it's the one that you have enough of, and not just enough, you've got too much of it. Okay, so this is the one that doesn't run out. Okay, you've got too much of it, and there will be some left over at the end. Okay, and I will get into this, but if you are ever asked to determine how much is left over at the end, you go, well, the moles that we had to start with minus the moles that reacted. Okay, now the moles that you have to start with, this will be, what color can I use? Sorry. The moles that you had to start with, this will usually be given in the question. The moles that reacted, you know how to do that, hey? If I tell you I've got 10 grams of this reactant, how much of this will react with it? It's just going to be a stoichiometry calculation. You use the mole ratios from your balanced equation. And that will give you the number of moles that are left over. Okay, then last off, our products. Okay, not much to say about that. We know what products are, but the amount or the number of moles of product formed depend on the number of moles of your limiting reagent. Okay, so they do not depend on how much excess reagent you have, because we didn't use all of the excess reagent. You use the one that we used up, which is the limiting reagent. Okay. I'm quickly going to pause you, erase this, and then we're going to look at the steps for how to determine the limiting reagent. Actually, before we do that quick, how do you know when there is a limiting reagent? So there's two scenarios. either they will give you a nice hint, they'll prompt you in the question by saying identify the limiting reagent. So if they've asked you to identify the limiting reagent, that means there is one, obviously, and then you can go ahead and find it. But they might not always say to you, find the limiting reagent. They can go straight into, here's your reaction, determine how much product is formed, and you first have to figure out which one of my reactants is limiting. Now we use this one's moles to determine how many moles are produced there. Okay, now how do we know when there's a limiting one? If they give you information about the amounts of both of your reactants. Okay, so if they tell you the mass of this and the mass of this, then you have to figure out, okay, wait. So they haven't told me which one is in excess. They've given me information about both, which means I have to figure out first which one runs out first. Which one do I not have enough of? Okay, so if they've told you the amounts of both of your reactants, and they haven't asked you to determine which one is the limiting reagent, it's a hint that you actually first have to determine the limiting reagent. Okay, not likely that they'll go straight into a question like that. That's a bit nasty, but you never know, they could. Okay, so I'm going to pause you, erase this, get rid of the cat, and then we'll go through the steps of how to do it. Okay guys, so here's our example. We've got the respiration reaction. So we've got glucose reacting with oxygen. They tell us we've got 25 grams of glucose and 40 grams of oxygen. They've given us the reaction equation, and question 1 says to identify the limiting reagent. So you have the steps on that note. So I'll just verbally say the steps and then do them. On the note, the step is written for each for each step that we do in answering the question as well. Okay, so first off, and this is something I want to address, it's not in that note, is I know that there are some of you who are going to look at these numbers and say to me, but ma'am, we have less glucose than we have oxygen, which means obviously then the glucose will run out first. No, okay, because firstly, remember that it reacts according to moles, not according to mass. So just because we have a bigger mass of oxygen does not necessarily mean we have more moles of it. You first have to convert it to moles, and then you'll see which one we have more of. But even if this were in moles, even if this were 25 moles and 40 moles, these do not react in a 1-to-1 ratio. For every 1 mole of glucose that I have, I need 6 moles of oxygen. So it makes sense that we'd have more oxygen than we'd have glucose. Hey, I need 6 times as much oxygen as I need glucose for this reaction to take place. Okay, so step 1 is first balance your reaction equation. If you don't even have a reaction equation, write it and then balance it. They've done that for us. They've given us a reaction equation that is already balanced. So we can move on to the next step. Now the next step is to take the information that is given to us and convert all of that into moles. Now I'm going to color code this slightly differently to the way that I did it on the note. I'm going to have all the actual physical amounts that we have, I'm going to do in red, and then the amounts that we need, I'm going to do in green. Okay, Mush, can you let go of me, please? Sorry, this cat is being very needy lately. Okay, so what do we have? So let's first look at glucose. The number of moles of glucose that we have is going to equal to the mass of glucose that we have divided by the molar mass of glucose. Okay, so it's the same as we would normally do for a stoichiometric question. Take the mass, change it to moles for glucose and for oxygen. Okay, so this would equal then 25 over 6 times 12 plus 12 times 1 plus 6 times 16. Sorry, I am writing quite small because I'm going to try and answer all of these questions on the one board without erasing anything. I don't know if that's going to come right, but okay. And when we do this calculation, we get 0,1388, etc., but we can round off safely to 4 or 5 decimals while we're busy with the calculation. Okay, now we're going to do the same thing for oxygen. So number of moles of oxygen is the mass of oxygen divided by its molar mass, which is, there's it, 40 divided by, now oxygen gas, it's O2, so it's 2 times the molar mass of oxygen. And I'm cheating, I'm using this printout so I don't have to use my calculator. And we get 1,25 moles of oxygen, and this was moles of glucose. Okay, now this is what we actually have. Now we've spoken already about the fact that what we need is for every 1 mole of glucose, we need 6 moles of oxygen. Now we can't really tell from these numbers if we have what we need. Hey? We need to know for every 1 of these, I need 6 of these. So the way we actually determine if we have enough is we say, okay, to get this to be 1, I would divide this by itself, right? So I must divide that by that as well, or vice versa. Okay, we want a 1 is to something ratio. So easiest way to do it really is to just set it up in a table. Okay, well, I'm going to have to erase some stuff. Okay, and we compare what we have. Oh, I said I was doing have in red. Okay, we compare what we have to what we need. Okay, now for what we have, for this step, we use what we've just calculated. And for what we need, we use these numbers here, the 1 and the 6. Okay, so we have 0.13889 moles of glucose to every 1.25 moles of oxygen, but we need 1 mole of glucose to every 6 moles of oxygen. Okay, so we're comparing what do we have in red with what do we actually need in green. And ratios, I'm not sure if you were, I don't think you were part of the grade 8 group where we did ratios in maths. I don't think so. Okay, but basically a ratio, so if you write a ratio of, I'm just going to do it up here, A is to B, that's the same thing as writing it as a fraction A over B. Okay, which I think you should know from doing similarity of triangles. Hey, the ratio of the sides, that means the fraction of the one side over the other side. Okay, so we're comparing the ratios, and to do that, we're going to write it as a fraction. So the first, and it's actually up to you, if you did oxygen before glucose, your table will look different, but your answer at the end will be the same. Okay, so I'm doing glucose first, so I'm going to say 0.13889. I'm actually setting this up differently to how it is in your notes. Sorry, let's first actually write, we're doing glucose first, and then we're doing oxygen, and we're doing it in the same order here. Okay, glucose first, and then oxygen. Okay, so when we go ahead and put it in a fraction, for have, glucose over oxygen, so it's 0.13889 over oxygen, which is 1.25. And we do the same thing here, the glucose number and then the oxygen number, and for this we use our balancing numbers. So this is 1 over 6. Okay, and we actually plug these into our calculators and we see what we get. Okay, so for the have ratio, we get 0.11, and for the need ratio, we get 0.17. Now the next step is to compare these values. If your, and I'm going to write this, okay, it is in your steps, but if your have ratio is less than your need ratio, then that means your first reactant is the limiting reactant. Okay, the first one you wrote in your ratio. So this means the first reactant is limiting. Okay, so it depends how you wrote it in your ratio. So this is the first one, this is the second one. And then if it's the other way around, if your have ratio is bigger than your need ratio, then your second reactant is limiting. Oh, this blue is running out, sorry. Okay, so because, now let's look what we've got. My have ratio is less than my need ratio. So we're going to write 0.11 is less than 0.17. So have is less than need. Therefore, glucose, our first reactant, C6H12O6, is limiting. Okay. So now we know which one is our limiting reagent. It's glucose. Okay, then when you know what your, this is a race. When you know what your limiting reagent is, then they could ask you to actually go and do a normal stoichiometric calculation. So they could say, okay, so now how much water is produced? Please do note that they could have skipped question 1 entirely and gone straight to how much water is produced. Then you need to actually do this first. First determine your limiting reagent, and then use your limiting reagent information. So we know glucose is limiting. That means we're going to use glucose in all other calculations, not oxygen. Okay, so the whole point of determining the limiting reagent is to figure out which one do I use to now do further stoichiometric calculations. So doing this has told us we use glucose because this is the one that runs out first. We're going to use glucose to determine how much water is produced. And that is question 2, is how much water is produced. Okay, if you haven't gotten this all down, pause me and quickly get it down because I'm going to erase most of it. I'm only going to leave this up on the board because doing this calculation has shown me this is the information that's important. Okay, so I'm erasing this, and then question 2 is to determine the amount of water produced. And that is a straightforward stoichiometric calculation. I hope you can cope with that, but I'll do it with you anyway. Maybe pause me and try it, actually, and then look. Okay, so question 2. I know it's not worded like this, but I'm trying to save space. How much water is produced? Okay, so we know we use the moles of glucose. We've already determined the moles of glucose. That's nice. Okay, so we can go straight to moles of glucose is equal to 0,13889. We've worked that out already. Remember, whenever you want to work out how much of something is produced, you change what you know into moles, you use reaction ratios, and then to determine the moles of what you want to know about, and then you change that into whatever they want. I think, what did they want here? Did they want mass? The mass, sorry. So it's not just how much, it's how much in grams. Okay, so we know the moles of glucose. Next up we go and use our ratios to figure out how many moles of water are produced. So we go glucose to water is a 1:6 ratio, okay? And above our ratios, we write down moles. So we've got 0,13889 moles of glucose, and we want to know how many moles of H2O we have. And we can now, from this, get a formula. So we can say the moles of H2O are going to equal the moles of glucose divided by 1, and then times by 6. Okay, which means the moles of water are going to be 0,13889 over 1 times 6. And where is my calculator? There we go, sorry. So it's 0.13889 times 6, and we get 0,8334. And now we check back to the question, what did they want? They didn't want mass. They didn't want moles, sorry, they wanted mass. So we take this, convert that into moles. So we can now go, well, the number of moles of H2O is the mass of H2O over the molar mass of H2O, and substitute in. So that's 0,8334 equals the mass of H2O produced, that's what we want, divided by the molar mass of H2O, which is 2 plus 16. Okay, so it's that times 18, and we get that the mass of H2O produced is 15,00012, so 15 grams of water produced. Okay, now this last question is a little bit trickier. The last question they've asked, well, how much of my oxygen is left over when the reaction is complete? So I'm going to have a reaction, I'm going to produce water, and because I had more oxygen than I needed, it means there's going to be some oxygen left over at the end. They want to know how much oxygen is left over at the end. Okay, so how much oxygen was in excess? How much of the excess reagent was in excess? So to do that, I did write it up on the board when we had the limiting reagent plus excess reagent goes to product. We wrote it under the excess reagent little reactant, and we wrote there that to find the number of moles that are left over, you take the number of moles that you have to start with and subtract the number of moles that react. Okay, so for question 3, they basically want the number of moles left over of oxygen. That's what they're asking for. Okay, so we know how many moles we had to start with. Oh, I've erased it now, but it was 40 grams. We worked it out on the right hand side of the board here in red. That's how many moles of oxygen we had to start with. Let me quickly grab it again. It was 1,25. Okay, so we know that this is 1,25. We want to determine how many moles are left over, so we have to first figure out, well, how many moles of oxygen are going to react. And it's the same process, okay? It's a normal reaction stoichiometry question. So we know the moles of glucose that reacted, 0,13889 moles of glucose reacted. And we want to know how many moles of oxygen then reacted. So we're going to do this whole ratio thing again. Okay, so we're saying, well, glucose to oxygen is 0,13889 to the moles of oxygen that react, which is a 1:6 ratio. Which means to determine the number of moles of oxygen that react, we take the number of moles of glucose, we divide by 1, and we times by 6. So that's going to be 0,13889 divided by 1 times 6. Oh, which is actually the same as for water. Okay, so that's going to equal, this blue coat is dead. That's going to equal 0,8334 moles of oxygen that reacted. Now, I just want to quickly check the question. Do they want to know the mass left over or the moles left over? Oh, they want the mass left over. Oh, no. Okay. Okay, so then we can actually just edit this equation. Okay, then instead of doing moles, much easier, we can say, well, it's going to be the same for mass. Eh? So the mass left over will equal the mass that we had to start with minus the mass that reacted. Okay, now we know the mass that we had to start with was 40 grams. And we now need to determine the mass that reacted. So if we've worked out the moles that reacted, very easy to go from moles to mass. So I'm going to just move over here. Sorry, trying to save space. So we can say the moles of oxygen that reacted is equal to the mass of oxygen that reacted over its molar mass. So I'm going to move sideways because I don't know how much of the bottom of the board you can see. So that means 0,8334 equals the mass of oxygen that reacted over 2 plus, oh, nope, sorry, this is not water, it's oxygen, over 2 times 16. So we've got 0.8334 multiplied by 32, and we get that the mass of oxygen that reacted was 26,67 grams. Now we can just go and put this here. Subtract it from 40, it'll give us the mass of oxygen that was left over. Okay, so still sort of trying to figure out how to use my space here. I'm going sideways. So from here we can say then that the mass of O2 left over is equal to 40, that's the amount we started with, minus 26,67, the amount that reacted. So we're going 40 minus 26,67, and we get that we've got 13,33 grams of oxygen left over at the end. Okay, a little bit of a mess on the board. The printout's at least a little bit more sort of organized in terms of its space and its layout. That's all I'm going to do with you guys. That's pretty much all that can be asked. So they can ask you to identify the limiting reagent. They can ask you to then use that information to do just a normal straightforward stoichiometry question, and then usually they don't, but they can sometimes then ask you like question 3 to determine how much of your excess reagent was actually in excess, so what was left over basically. Okay, you're going to do those questions at the bottom of that printout for me, and then for the next week actually I think it's only 2 days, yeah, for the 2 days after. So Tuesday you're doing this for me, then Wednesday and Thursday you're going to do just sort of past paper questions on all of stoichiometry. This is pretty much the only thing that's new, I think, this and dilution is quite easy, so I'm hoping you can cope with it. Master it, make sure you've got it, because we are then moving on to electrostatics after this, and I hope that you've done some revision of your grade 10 electrostatics. Well, this is a long video, sorry guys.